Lab 3, Black Hole Orbit. The goal of this lab is to find a mass of a black hole respective to a star in orbit using Newton's gravitational force law. For this lab, we rearranged Newton's gravitational law in order to find the mass of the black hole. I was given the position of the star. I used 6.67 times 10 to the negative 11th as the gravitational constant, and I had to calculate the net force using my knowledge of the momentum principle. I further calculated the magnitude of the radius between the star and the black hole, and from there was able to solve for the unknown, the mass of the black hole. From doing these calculations, I was able to obtain a mass of 3.41 times 10 to the 31st kilograms for the black hole. Newton's gravitational law states that the net force is equal to the gravitational constant multiplied by the mass of the star and the mass of the black hole, all divided by the radius between the black hole and the star squared. To solve for the mass of the black hole, I rearranged this equation. This means that the net force multiplied by the radius squared and all divided by the mass of the star will give us the mass of the black hole. I started by inputting my initial conditions into the code. The mass of the star is 1.989 times 10 to the 30, and the position of the black hole is a vector of 1 times 10 to the 10 in the x direction and negative 1 times 10 to the 10 in the y direction. The change in time is 1 day, or at 864,000 seconds. We were given a CSV file to read the position data of the star, which would then be used to calculate initial and final velocities. In order to calculate the velocities in the x and y direction, we subtracted the initial positions from the final positions and divided that by the change in time, delta t. In order to find the net force, I had to start from the momentum principle. As you can see from the code, the initial and final velocities were used to find the initial and final momentum. The total momentum is equal to the mass of the star times the final velocity minus the mass of the star times the initial velocity. From the momentum equation, we can infer that the total net force is equal to the change in momentum over the change in time. Net force is split into parallel and perpendicular components, and therefore so is the change in momentum over the change in time. This means that the total net change in momentum over the net change in time is equal to the change in momentum over the change in time in the parallel direction plus the change in momentum over the change in time in the perpendicular direction. Rearranging this, we can find the perpendicular component of the change in momentum over the change in time. Looking at the code, dp over dt is equal to the net force. We should not forget that p hat is our unit vector, which is the initial momentum over the magnitude of the initial momentum. dp over dt in the parallel direction is equal to the magnitude of the final momentum minus the magnitude of the initial momentum divided by delta t. dp dt in the perpendicular direction is then just dp over dt minus dp over dt in the parallel direction. To find the radius, we want to find the magnitude of the difference from the star's position to the position of the black hole. In order to do this, we take the difference from the black hole to the star, and then we take the square root of the x value squared plus the y value squared. After rearranging our formula like stated before and plugging in all known values, we find that the net force is equal to 1.476 times 10 to the 27th newtons. The distance, or the radius, is 1.75 times 10 to the 12th meters, and the mass of the black hole is 3.14 times 10 to the 31 kilograms. Our computational model shows us a visual of the star orbiting the black hole and the net gravitational force exerted on the black hole by the star. The black dot represents the black hole located at a respective position. The black arrow represents the parallel force, the blue arrow represents the perpendicular force, and the yellow arrow represents the net force, which is always pointing towards the black hole because the parallel and perpendicular forces equal the net force. The net force and the net force in the parallel and perpendicular directions are different from dp over dt, also in the perpendicular and parallel directions. Fnet is found through Newton's gravitational law. It can also be found by summing the individual forces. However, dp over dt is found through observing the motion of an object and its change in velocity. Although they are equal in the momentum principle, they are found in different ways and are therefore not the same. Given the scenario, if a different hole was placed in the same location, assuming the motion of the star is unchanged and is only affected by the gravitational force, then no, one would not be able to tell the difference. Nothing has been changed except the black hole, and therefore Therefore, the velocity, position, and momentum are the same for the star orbiting, and the net gravitational force will not change.